and I literally popped in and ended up in this room. So happy to be here. I don't have a
Right.
lot of questions, but it's good to see you. And how
Yeah,
are you?
I'm fine. I'm wondering how Clubhouse is, increasingly, because, like, for
Well,
example, I can't. I, being of limited intelligence these days, find it increasingly difficult to find out how to find live rooms. I can't find the hallway anymore, for example.
I hear you. I
I don't know
can't
how to do it.
find.
I really
Yeah,
don't.
I don't know. It's. I mean, I remember back. Of course, we say, but back in the day when, you'd have a couple hundred people in the room, and
Right.
and lots of party hats and newcomers and old timers and just I don't know, Dr. Laird. It's just things always change, and uh,
Yeah.
you roll with it until you roll someplace else, or you know,
Yeah.
come to a
Yeah.
stop.
All right, so let's see if we can. So why don't Lois? Why don't you tell the folk in the audience what I'm about and invite them to the stage?
Sounds good. Well, listen, guys, you ended up here in, well, first, this is Small Steps and Giant Leaps, which is been around for a while here on Clubhouse. And this is Dr. Laird Whitehill, who is here to answer our stupid or not so stupid or ingenious or, lighthearted questions or about astronomy or astrophysics, right, Dr. Laird?
Right, and basically, I love science, so
Mm-hmm.
it can go beyond just plain old stupid astronomy questions. It can get on to all the realms in which human beings can be stupid, uh, as related to science, but mostly science, mostly astronomy, of course.
This is, yeah, and right. No, look, we've got GPT. We have Google to answer if we can't figure it out. Um, there has been live research done on this channel before, and can be done again. So, guys down in the audience, raise your hand. Um, and come up on stage and just enjoy the time that we have together because there's no time like now.
Okay, thanks, Lois. So great. We have Haris, who is often on the stage, and Jack, who I know to be laying in bed with a good case of pneumonia, and so Haris, welcome to the stage. Uh,
Good evening.
yeah.
I have a question. It first popped up for me a few weeks ago, but more questions then, and so it popped into my head that to ask this week, and it's this. I read an article that an internet company here in the states is putting a 10 foot tall satellite into space that would serve this hemisphere. And they're putting
Hmm.
it in an orbit where it basically is stationary so that, as signals bounce to it and off of it,
Hmm.
it's it's sending signals back to this hemisphere, not, going into spinning orbits like the International Space Station. And I'm wondering if you can explain to me, like, what is the I don't know, relationship between a spinning planet and the space around it that some like objects like the International Space Station will go at whizzing speeds around the planet, but at different levels, apparently, you can have a
Hmm.
satellite that's basically stationary.
That's a very it's a good question. It's an interesting question because the idea that something can be stationary and yet in orbit is
Right.
kind of sort of weird. But of course it's possible because the Earth spins. So all you have to do is match the rate at which the Earth spins, and you stay above the same spot over in the Earth. Now, in truth, if you're trying to that stunt, The word hemisphere in this case, while true, refers to not the hemispheres east, north, and south, but east and west. So you can stay over a hemisphere to the east or hemisphere to the west, but you have to be hanging out at the equator when you're doing this. If you're doing any other orbit than that, you're not. You are going to move back and forth across the sky, even if you're
Mm.
even if you're traveling around the Earth at the same speed at which the Earth rotates, you're still going to move back and forth across the sky. If you want to be able to be received by Earth-based stations, which are not busy pointing back and forth, then you better be directly over the equator, and you will never move in the sky from time to time. The height that you have to be at is 23,000 miles high, whereas the space
Oh,
station
damn.
is
Oh.
350 kilometers or miles, I forget now. And it's funny because so that's not news to you, right?
I didn't realize. I never really thought of like how high up satellites go. I just didn't think 23,000 feet.
23,000 miles.
Miles in it. I'm sorry.
Miles. The Earth's diameter is 8,000 miles. So
Right.
that's pretty high up. Whereas space station is just a teeny bit higher than the Earth's, is just above the Earth's atmosphere. The, a space station that's up there 23,000 miles is way beyond our atmosphere and, and will never come down. It will be there for basically uh, a very long time until something terrible happens, like to the sun. It's going to be up there for millions and probably billions of years before something might bring it down, like decay brought about by micrometeorites could bring it down over millions of years. But the Earth's atmosphere will not be a part of that. There's no atmosphere up there, whereas there is atmosphere near the Space International Space Station. So they have to periodically boost it higher.
I do. I have read that where like sometimes the atmosphere starts pulling it in, and they gotta thrust themselves back out. So like at different levels above the atmosphere, going further out, does the I mean things spin at different speeds around the planet?
Yeah, the further out you go, the longer it takes the thing to go around. Uh, you know of one particular object, and you know how long it takes to go around. Besides the International Space Station, which goes around once every hour and a half, can you name another well-known object that takes longer to go around the Earth? Okay, time's up. Uh,
Yeah,
the answer to
you always
the answer to
stumped
that
me on
question is the answer to that question is the moon. It takes a moonth. It takes a
that.
moonth to go around the Earth.
Oh, that's funny.
Right.
I guess what was it the nature of I guess space above the planet that things spin at different velocities depending on how
Right.
far out you go,
So there's so
or is that an
there's
optical illusion?
well, no. It has to be true. Think about this: like if something's up there, right,
Mm.
and nothing is bothering it whatsoever, then according to the laws of physics and your common sense, something would keep going straight in a straight line forever. But what happens if there was a little thing called gravity? If there's a little bit of gravity, right, then that thing will be bent by the gravity. And
Mm.
so if you do it just right, then the gravity bends it just the right amount for it to continually go around in pretty much a circle. If the thing is moving too fast, it will it will escape Earth's pull. If the thing is moving too slow, it will fall down And like if it wasn't moving at all with respect to the Earth's surface, from the point of view of something looking straight up, if it didn't move at all, then it would fall right down and hit the Earth. So there's varying speeds that you have to travel at. The If you're traveling at the as like the International Space Station, you're traveling around 18,000 miles per hour. I think actually less than that, more like 17,000 miles per hour. And you travel around in an hour and a half. Interestingly, if you dug a hole in the earth and dropped something through it, it would end up back where you dropped it from an hour and a half later. So it's which is kind of funny, but it's true also. I always think of Elon Musk as having created his the idea for this boring thing where he digs a tube under the ground and he
Mhm.
lets uh, something drop, and then it would fly from Los Angeles to San Francisco. Well, if it was a perfectly hollowed out vacuum and he just let it drop, it would take an hour and a half to fall from Los Angeles to San Francisco and back again if it was a perfectly hollowed out tube and straight. So any tube through the Earth will, I think, take an hour and a half for the object to fall one way through the other. So it's not just Earth satellites that obey certain weird laws of physics. And the other thing that's interesting is about the international about geostationary satellites is that if you could find the strong enough materials, you could drop a ladder from that satellite all the way to the Earth's surface and climb up it all the way up to the geostationary satellite. That is a real thing that physics would allow with some additional constraints. But it's called a space elevator, and it's realistic for such places as the moon and Mars. But in current day, it's not realistic for the Earth because we haven't figured out something strong enough that would be able to withstand the Earth's gravity for the entire length of the 23,000 miles. So nothing is strong enough. But maybe one day. And then maybe we'll have a space ladder.
Because I remember the Japanese were reading articles a few years ago. The Japanese were thinking, we're trying to devise such a material that could do that.
Right. And so far, nothing has.
Yeah.
I think the strongest candidate is either carbon nanotubes or spider silk. One of those two things.
Thank you for that. That was a great explanation. One other question I had this week is, can you explain Einstein rings?
Yeah, uh, I can. And I'm just inviting a few people to speak as we. So just what I'm doing right now, I will. But right now, what I'm doing is I'm touching everybody's button and inviting everybody to speak so that you could all be equally embarrassed if you would reject my invitation. Uh, nobody's being singled out uh, to be invited to the stage. Oh, it's interesting. I can't when I'm pressing certain buttons, odd things happen. That's odd. Okay. All right. I've invited pretty much everybody, with few exceptions, to the stage, and it's on you if you don't come. Uh, in the meantime, Einstein rings. Uh, so, so basically, if you put something in front of your face, you can't see behind it, and the reason for that is uh, because light travels in straight lines. So basically, you're you don't have a wing or a prayer. But if the thing that you happen to place behind, in front of your face, happened to have a very strong gravitational pull, and it didn't happen to bother you very much, say, like for example, the thing that you put in front of your face isn't close by, so it really doesn't bother you. Uh, and we can discuss not being very close by in the sense of that object could be billions of light years away. Billions of light years away. Why not? So, billions of light years away from your face, there are these things called galaxies, and even these things called clusters of galaxies. And so they have the property of lots of gravity and not bothering you. But any light that's being emitted from objects behind them can be bent around them and then be focused towards you. And if you imagine a perfectly, beautifully homogeneous object like a giant tennis ball instead of a giant galaxy or cluster of galaxies, then and if that giant tennis ball of cluster of galaxies was placed appropriately, you would see a ring around that cluster of galaxies. In practice, what you see is series of arcs, never a perfect ring, but some come pretty close. And those are called Einstein rings. Einstein, because he invented gravity, or at least described it accurately for the first time.
Wow, neat. Okay.
Hmm.
Thank you again for your explanations. It always great.
Thanks. No, no, really, I appreciate you coming up to ask. Uh, that is that's the thing that uh, we need. Okay, so Harris, let me see something. I want to see if I can find your profile. Okay, so this is interesting. Uh, your profile, if I'm right, uh, is a single paragraph, uh, and I am I have noticed that Clubhouse was not providing uh, uh, profiles anymore. But I think if that's your profile, that's very good. I just want to check. Frankie, I'm going to check your profile and see if it's there. Theatrical puppeteer is all it says. Uh, I need the profiles for this room because in order for me, and so I see there are profiles, they're back. Okay, because they weren't there the other week. And without profiles, I really can't tell as easily where you coming from. Uh, so, so in this case, your profile is does not indicate. Oh, there it is. Degrees in cultural anthropology and political science. So yeah,
Mhm.
what does code switch mean? Don't code switch with me.
Oh, it's like I go into a lot of different rooms with diversity, different diverse groups, and um, sometimes people feel the need to uh, uh, you know, talk differently when someone that's not part of the group is there, and so it's just a way of saying just be yourself.
Oh, well, there you go. See, I didn't understand that. Okay, that's interesting eh, because I didn't understand it. Do you want to explain that further, or would you just leave it?
Um, if it's just be yourself around me rather than
Be yourself. Is that the idea?
yeah. More specifically, it's a term more common in like the African American community, where they feel the need to um, talk more white when to white employers
Oh,
or people,
oh,
so that there's more depth to it, and sometimes like when I'm in a room that's African American centric, I've noticed people changing their language or how they speak when to me or around me, and so it's my way of both acknowledging that they need to do this around some white people, given the context. And it's my way of saying you don't have to do that around me.
Well, you know, in this room, I'm code switching because, uh, for one thing, uh, my persona in this room is somewhat authoritarian and somewhat, you know, gee, I know all this shit and you don't. So hence your stupid astronomy questions. And, and of course, in real life, I can't get away with any of that. Uh, uh, so I'm not so sure that I'm not to blame as well. Uh, but and so I don't know. Is it so bad to become different in front of different people? Is that a bad thing?
Or if it's felt to be obligatory, rather than something natural. Then
Uh
you're
huh.
then like because then like that person is changing themselves for me, and that
But maybe you wouldn't understand. Maybe you wouldn't understand. So maybe that they want to be related to, and they figure that if they code switch, then they can uh, have a better conversation with you because they're, if you will, not uh, talking about things that you don't understand.
theoretically you're absolutely right. Just culturally, as it's normally practiced, particularly in the Black community, um, it's it's more of a requirement, or it well, promise not the right word. It's more I can't change me on the
But
what's the right
didn't
reference.
Obama code switch?
Uh, I, I think, well, I mean, he grew up with a white mother and a white family, so he didn't.
No, but
Uh,
when he came into black communities, didn't he sound more black?
Bingo, that's code switching to the nth degree. Yep. You know that one. Yep. And the he got a lot of flack for that because that wasn't the way he normally spoke. Um,
Right.
and a lot of people felt that he was pandering to them in an attempt to quote unquote sound black. Um,
And then don't politicians code switch for a living?
Depends on who their target market is. If their target market is uh, well, code switching is switch is the operative words. I mean, it's one thing to tailor your language to who you're talking about. If you're talking to suburban white woman versus um, inner city black people, your tailoring is one thing, but really switching your persona to try to match the audience is where it becomes disingenuous and becomes um, uh, you know fake and pandering. But considering Black Americans are 14% of the population, uh, particularly in the workplace, they feel the need to sound white so that um, their bosses feel more comfortable with them. Their coworkers feel more comfortable with them um, because you know many white people are uncomfortable around black people, and so they're changing themselves for other people's benefit that doesn't provide any to them. So that's where it's you know the switch is it's more of a switch than the tailoring because this isn't how they would normally talk um, as it would in their own homes or with their own friends.
I'm from New York City, and I have learned over the years that my accent, especially uh, uh, some parts of my accent, are really uh, don't serve me well. And so I really do try. So I think I'm equally liable for doing that. I don't get it. But anyway, that's just for
I
the fun
appreciate
of
your
it.
question.
Yeah. I'm hoping that we have more volunteers. Uh, as I said earlier, uh, my son-in-law, who was Jack, I'm not sure he's able to speak at all, but I do know that uh, he's not feeling well, so I can't expect. Oh, there you go, Jack. How are you feeling?
I'll try to do my best.
Uh-huh. Right. Well, yeah. Uh, uh, so maybe the folks in the room can help diagnose your your disease. Maybe instead of talking astronomy, we can talk about illnesses. Do you want to see if the people in the room have any suggestions?
The doctors I've been seeing seem to think that they know what's wrong with me,
Oh,
but
really?
that's but we could crowdsource my
Yeah.
non-working lungs. Sure, why not?
Yeah. It's long. It's been going on for a while. It's been do you have a diagnosis?
Yeah, I yes and no. I had pneumonia, and as of today, now they don't think I have an infection anymore, but they think my lungs don't work properly. So they're trying to figure out why.
Mm. Oh, so it's no longer treatable with antibiotics and magic drugs. It's or the usual things. It's something else entirely.
Yeah, you and I actually have something in common where I now have the same oxygen levels that you had when you had COVID. I
Ah,
scored an 88 on my oximeter,
that
which
is
is
not good.
no fun.
Are you still coughing?
Oh yeah,
Yeah.
but not in a way that indicates that I have uh, um, like a fluid in my lungs.
Mm, mm,
But
right.
this is not why I'm here.
Okay. Why are you here
Well,
tonight? Besides keeping me company.
uh, this is Z chiming in. I was just wondering if you maybe ask, first of all, uh, your doctors about uh, anything wrong with your diaphragm at all. As your like, is there something wrong with your diaphragm, or you're not able to take a deep breath, or you're getting over infection? Like, what's yeah?
We went through a series of X-rays today. On Friday, I go through other tests, and then next week they'll be um, going through all of that to figure out to see if a certain number of medications they put me on right now are will work or not. So
Are you
Uh,
taking any tea? Like something that comes to mind is, I know it sounds, is something called mullein or mullein tea, uh,
I'm
which
not
is
familiar with that. No, I'm on steroids and
steroids. Yeah.
different types of uh, again, not this is not what I was hoping to talk about when I entered an
well,
astrophysics chat with Dr. Laird.
Hey.
all right. So but Jack, the reason I did that is because I haven't spoken to you in a couple of days, and and I am concerned. But what were you hoping to talk about, if anything, related to astronomy?
I was hoping to talk about rogue planets, if you don't mind.
Rogue planets.
Rogue
That
planets.
I love rogue planets.
Oh, good.
Uh,
NASA seems to think there's more rogue planets in our galaxy than there are planets that orbit stars.
yeah,
And
yeah.
I forget the name of their telescope they're going to launch in a couple of years, I think in 2027.
Yeah, I always forget it too. It could be the Vera Rubin. It could be,
Yeah, I think that's.
or not that one. It's the other one, named by for a woman as well. Um,
Yeah, so what they were saying, though, is that they are thinking there could be hundreds of Earth, um, like rogue worlds.
right.
Um, and I'm wondering how is it possible to have an Earth rogue world? How is it possible to have a world like Earth that's not orbiting a star.
Okay, so that is a great question actually, and it's interesting because the because first of all, I think it's absolutely well established that there are these rogue planets, and the only thing that needs to be established is the how many of them there are, and but the question of why is quite clear, and that's an interesting story. The when we were all brought up with nine planets, and and then a few years ago, long before Pluto was demoted, uh, it was it was found by computer simulations that it is possible that that Uranus and Neptune changed places at one point in the history of our solar system, or that Saturn, even perhaps even Saturn or Jupiter, have moved in our solar system. So the way the solar system is set up right now is nothing like the way it was set up when the solar system was first being formed. So at the time that the solar system was being formed, there were these rogue planets roaming our solar system. There were many more than uh, just the nine planets. Many, many more. And some of those hit, well, one of them in particular hit the Earth. We have a word for that planet. That, that planet's name is Thera. And when Thera hit the Earth, it formed the moon. So there's one well known, well thought of planet that didn't leave our solar system but became absorbed by our planet. But for every planet that was absorbed by other planets, there were many more that were thrown out. Again, in terms of planets being absorbed, there's a very deep basin on Mars, perhaps the largest crater in the solar system, but it's not doesn't look like a crater; it just looks like a depression. And that's a rogue planet that hit Mars. So aside from those planets that hit each other and were absorbed, there were others that just roamed the solar system, but they were in unstable orbits. And what that means is that Jupiter would have a little bit to say every time it passed by Jupiter. And it would have to eventually make peace with Jupiter. And the way you make peace with Jupiter is you make sure to avoid Jupiter whenever you're in the same vicinity of the orbit. So you don't want to be there when Jupiter's there. For those planets that didn't know better, they would be nudged a little bit at a time. And, millions of years is a little bit of time, but it's a short period of time in the history of the solar system. So our solar system, let's say, got itself put together in say a million or 10 million years, but there was 4,500 million years that the solar system was busy doing its thing before we came around. And long before then, there were planets being tossed hither and thither, and the ones that didn't behave well got thrown out. Those were called monarchs. That's an actual word for these planets when they were here and then gone. Monarchs. And it is said that the solar system, in one thing I read, the solar system had hundreds of monarch planets during its early phases, which conforms to the idea that now there are many more planets out there than there are planets circling stars. So, and of course, these planets could be of varying sizes. They range from, you know, the size of grains of sand to all the way up to what? Stars. In fact, there's a complete range of objects in the universe, and they orbit and they travel at different orbits. Some are bound to orbit each other, and they're called double stars. Some are if you have a triple star, for example, one of those can be thrown out if it's not behaving well. It just takes three objects to throw one of them away. And you had, if you will, nine objects in our solar system. So it wasn't hard for our solar system to dispose of any unruly planets that were created at the same time. So there's no way that there can't be Earth-like planets containing just the same stuff that ours did. All the right elements for life, except, of course, that it would be then a frozen rock. So what do
That's
you
the
get?
crux of my question, which is how can you, what can you do with a rogue planet that's just like Earth but doesn't have a heat source?
But the thing is, they all have heat sources. Well, not all. If you interview all the planets that are out there in the universe, okay, and you ask them all the same question, how hot are you inside? The answer depends upon where they were born. If they were born inside a solar system which was the product of the gases thrown out by previous supernovas, like our star was. Our star was the product of previous supernovas and the gases that were created in those explosions. And not only supernovas, but it's now known that our sun was also created as a product of the explosions of kilonovas, which are neutron stars that have collided. So, so all the gold in your teeth or in your necklaces came from kilonovas. So, but not only gold, but also uranium and the radioactive elements as well. Inside our Earth, it is very hot down there. It gets hotter the further you go down. And the reason for that is not what you would expect as being something simple like, well, the deeper you go, the hotter it gets. Well, the reason for that is because the deeper you go, the, the heat released by the decay of radioactive elements has yet to get to the surface after 4.5 billion years. It's still making its way up. So the inside of the Earth is cold, is warm, and so you don't have to go down very far before any possibility of ice disappears. So on pretty much every rogue planet that was born in just the right kind of cloud, you will find a transition from ice at the surface to liquid water as you go down further. And depending upon the amount of water, you could have an ocean, a liquid ocean, a liquid ice ocean, and that a liquid ice surface covering a perfectly normal but completely covered ocean as far down as miles deep. And then further down, you would find these things, perhaps these black smokers that we have on our planet. And we find life down there. And we find life that seems to be based upon a different mechanism than the life at the surface. So it's entirely possible that many of these rogue planets, if life is in fact the rule rather than the exception, then it's quite possible that these rogue planets uh, uh, harbor life, each and every one of them. It's possible that Enceladus in our solar system harbors life. It's possible that Europa does. It's possible that Ganymede and Callisto harbor life. It's possible that Pluto and Charon harbor life because they have liquid oceans below them. So there are many places in our solar system which are known to have liquid oceans below. And so it's likely that all of those rogue planets, many of them, would also have rogue planets, life as well. Assuming, of course, that life is the rule rather than the exception. So it's something that unfortunately I and none of you either will ever learn whether it's true or not that life is the rule rather than the exception. I don't think our our studies of Mars will indicate that, uh, and our studies of this mission to uh, the asteroid Bennu is going to reveal that either. So we may never know for a very long time, if forever, whether life is the rule or the exception. It may, in fact, take supercomputers of an unknown power that will answer the question ultimately whether the life is the rule or the exception. But I think I just went all over the place with that. Uh, but I do like the idea of planets being thrown out of solar systems. It's it's just a magical thing, and I'd love to see it as a movie. I've never seen a movie like it, but why not? Somebody could tell the story of the universe in in a big, long, semi-science fictional way, and I would buy every bit of it. So, all right, okay. So that was my little thing on rogue planets.
You
Uh,
said our exploration of Mars will probably we is not going to be where it needs to be for us to have an understanding
yeah,
of life there in our lifetime.
uh, yeah.
But have you been have you read recently what NASA wants to do with 3D printing
Well, they're
and
always
how
planning on 3D printing stuff on Mars, but no, what do you mean?
their goal now is in the next 20 years to build um, human habitats on the moon
Hmm.
using 3D printing and the resources they can find on the moon, and then use that as a jumping off space to do the same thing in Mars, essentially making it a goal that with, well, hopefully my lifetime, given how my lungs hold up, um,
Yes.
that they could put a community on the moon in the next couple of decades.
Well, I'm not. I'm not. I'm hopeful that we will. I'm certainly hopeful that we will make it to Mars and dig a hole and bring the stuff back uh, to Earth and get a chance to examine it. I think it's likely that we will bring stuff back from Mars before we go there with people. And but my objection to finding life on Mars has nothing to do with whether or not life is on Mars or not. I uh, I presuppose, for the purpose of argument, that there is life on Mars. But I also but I also presuppose, for the purpose of argument, that that life is just like ours in the sense of that it's built with a DNA backbone. And and therefore, if those two things be true, then uh, then it would be, in my opinion, thirdly, impossible to determine whether that life had an independent origin from our own. So again, I say there's life on Mars for the purpose of argument, that it has a DNA background, and that we'll all be very disappointed because we won't be able to argue successfully that it was developed independently. So we won't have answered the question whether life is the rule or the exception in the universe. That's the sad part of the story I just told. And if any part of that be wrong, well, that'd be great. And the best thing would be if life was found on Mars and it had a different type of DNA built differently than the way we build DNA. They have experimented with building DNA differently than the way that it's built. And so they have. Uh, I'm not a biologist, and all the biology I've studied is gone, but I do know that they have tried different ways of building it, and and they have been successful in the sense of understanding that it can be done, but also unsuccessful in realizing that it could work. I don't remember why it can't work, uh, but it has to do with the very, very well done way that our backbone is constructed. It's a double helix, but it's not just a double helix. It's also the way that, remember, if you have a double helix, what's really true is it has to pull itself apart in order to reproduce. And then each of those individual pieces of the helix need to pick up daughters and sons and reproduce themselves and produce another set of DNA. But the way that that chain uh, uh, rotates around the DNA, that is a backbone, and that backbone can be invented to be different using different elements, and they don't work as well. Ours so far, to our knowledge, is the best one that nature can invent. So I imagine, again for the purposes of argument, that we have the best DNA that nature can invent, and that nature will never do a better job of it. So that if we find life elsewhere, it will have DNA, again, a supposition, and therefore we would have to be able to say without fear of contradiction that it was independently evolved. And that, if that be the case, we'd have to probably go as far as Saturn before, and the moon Enceladus, before we could be dead certain that it evolved independently. Which is why I'm really interested in NASA uh, 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 green lighting a mission to Enceladus. Enceladus is a great place to go. Uh, it's it's uh, it's certainly twice as far as Jupiter, but the good thing is it's got active ice volcanoes that are constantly spewing ice crystals into the interplanetary space, and all a spacecraft has to do is whiz by, scoop up some ice crystals thrown up by these volcanoes, and then if it's an Elon Musk rocket, turn around and come back to Earth and bring that stuff with it so that we can analyze it here. I see that as being something that is much more, uh, it's easier to do than putting people on Mars, and would answer the question of whether life is the rule or the exception much more definitively. So I'm all for a Enceladus mission. Let's cancel Mars. Uh, and Mars isn't a good place to live anyway. No trees. So we'll see. And you can launch these things from the moon if you like. So let's go to the moon, but let's skip Mars and go to Enceladus. My point. Okay. So having ranted about that, uh, uh, what else would anybody like to say good, if not Jack?
Yeah, hello, doctor. Yeah, I'm really interested to know, like you talked about Enceladus. What is this concept of global ocean on Saturn's moon?
Um,
That was talked about
be
this
more
Cassini
specific.
mission.
Me, talk some more. What are you asking?
Yeah, means when this Cassini mission talked about this structure of this Enceladus, so they use this word, global ocean,
Global ocean, right?
yeah, on Saturn's moon. So what does that indicate?
What does it indicate? Is that what you're
Yeah,
asking?
means yeah, means what is there in that ocean means not necessarily water or something, means they
No, it's
use
it's
the
water.
term, yeah,
It's
they use
water.
the term global. Oh, wow.
I see you have an icon that looks as if you are a sailor. Is that a steering wheel from a sailing ship in your hands?
Yes, kind of.
Uh-huh. Do you have a special relationship with sailing ships?
No, 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 no relations as such.
Okay. All right. So sailing ships uh, are not obviously possible, uh, but the below the ice level, ice layer, which can be miles thick, there can be an ocean of water that can be also miles thick. Now, that's what I said. What did you want to know about that?
Yeah, I mean, I was just trying to know that why they use this word global, not just calling it a water ocean or something like that. They said that this is a global ocean.
Because it would be it covers the entire planet from one end to the other. Actually, on Enceladus, Enceladus uh, is if you look at that moon, some parts of it are different from other parts of it. This one part of it has this thing called tiger stripes, and the other part of it does not. Both parts of all parts of that moon are freshly fresh surfaces that don't show the scars of impacts with with meteors. They have long been erased, so that that surface is clearly ice that has been constantly re-established from water underneath. And so the water underneath is responsible for keeping the planet uh, relatively free of craters. Now I said planet, but I mean moon. And global ocean because it would be true that that ocean would be everywhere underneath the ice, with maybe some exceptions if that's not if what I said is not right, but certainly that's the idea that it's global. Do you have a problem with the word global? I don't understand.
No, no, no. I don't have a problem, but I was in a misconception that it is not easy to find water outside this Earth Mars zone. But when you were discussing with Jack, then I got this discussion. That
Uh,
means that water is readily available, but life may not be there. That kind of
right,
thing was coming to my mind.
right. Water is the rule rather than the exception. It's found everywhere, and and so it's not surprising that when we look up into the rest of the universe, one of the things that we do find fairly easily with our advanced telescopes is the presence of water. Water is the first thing. So water on Earth is surprising because when Earth was being formed, it was too hot for water to condense into a liquid or a solid. It was still a gas, and the Earth's gravity wasn't strong enough to pull that water down from the heavens. So our planet was, it is thought, and not necessarily proven, that our planet was devoid of water during its formation. So that the water that we have on our planet needed to come from someplace else, and the someplace else would be where the place in the solar system which is far enough away from the sun so that the so that the ice water can form as ice. So they call that the frost line, and any object forming beyond the frost line would have a large quantity of water. So, for example, uh, comets, which invade our solar system from far away, have an awful lot of water in their composition. But some asteroids that are below the frost line, inside the asteroid belt, are not necessarily composed of very much water. So it's supposed that the solar system had an awful lot of these watery bodies in the early part of the solar system. And when the solar system was mixing it up with all these rogue planets and monarchs and uh, and planets like Uranus and Neptune switching places, that these watery asteroids rained down on the inner solar system and and provided the water that our planet has now, as well as creating some of the large craters on the moon. It is thought that that same process that may have brought large craters to the moon, also brought water to the Earth. So, so it's water is the rule. Look, hydrogen is makes up most of the universe, and then oxygen isn't far behind. I mean, it's mostly hydrogen with a little oxygen, but nevertheless, and the oxygen has to be made inside of stars. You don't get oxygen without nuclear fusion, but with enough nuclear fusion, you can get all the water you need. And thank you, Z, for putting yourself in the audience. Uh, again, water is the rule.
Wow. So you mean to say that water is not necessarily a local phenomenon, mm, but coming with the regular process of the life of a star as well, around the universe.
Say that again. I didn't quite catch it.
Yeah, yeah. I mean to say that you mean to say that water is so obvious that it may happen or it may be there happening regularly, with the life of stars and different stars, water and oxygen.
Right. Well, water not on stars, but the oxygen that that the water is made out of has to be made inside of stars. But stars are very happy to oblige because stars blow up and have been blowing up for billions of years, seeding the interstellar environment with lots and lots of oxygen. And it's hard to find stars that don't have oxygen in their outer layers that were provided by earlier stars that blew up. So if stars have oxygen, the planets that formed at the same time that the stars did will also have oxygen.
Yeah, and will they have this oxygen cycle as well, the way we have on Earth?
Well, you said oxygen cycle, and what do you mean by oxygen cycle?
Means that's the biochemical. No, that's a biochemical process, like what we read here
Well, for example,
from the context of Earth.
our planet didn't have oxygen when it was first formed, it's thought. Our planet was devoid of oxygen. It is, I mean, we had water, but uh, we didn't have oxygen, uh, and and any oxygen that was found uh, on our planet was greedily eaten up by iron. Iron is quite good at sequestering oxygen, and we call the resulting compound rust. So, so for a long period of time in the history of the Earth, there was any oxygen that was available was sequestered as iron oxide or iron ore, as we think of it today. And and at the same time, uh, uh, there was life that is thought to have been based on a non-oxygen environment using methane or even sulfur, and and it the those early life forms created an oxygen atmosphere, which we now enjoy. But oxygen initially was poisonous to life as we know it, and life only subsequently learned to use oxygen in its as an energy source, as a way to oxidize and create energy uh, to make fuel for the cell. But in the early days, the early life forms didn't use oxygen. Now, again, this is biology, not, and I'm, I don't know enough biology to be talking about it. But again, I'm not sure I'm answering your question.
Yeah, it's, that's that is certainly generating some curiosity for sure. Like you use the word poisonous means why was so
What is the word I used?
poisonous? Like oxygen was poisonous initially for life.
Right. Oxygen uh, is uh, is a poisonous gas if you happen to be a life form that is has never encountered it. It's an oxidizing agent, and the thing that it does very well is make fire, right? Well, of course, it would there wouldn't be fire, but it would set fire, if you will, to the internals of a cell because it's able to oxidize, which means combine with chemically anything that would be in the early cells. So it would destroy the early cells. So the early cells did not have to contend with an oxygen atmosphere. But over a period of time, they produced oxygen as a result of their the chemical processes. Photosynthesis produces oxygen, but certain organisms learned to use that oxygen to burn the energy stores in their cells. So it took a while for oxygen to become, in fact, the thing that sustains advanced life forms on this planet. Now, I wish there was somebody in the audience who knew something about the biology I'm talking about who could help me here, because this is interesting, but I haven't studied this in quite a while. Do we have any incipient biologists in the audience who'd like to come to the stage and help me with this story of of the history of life on this planet? No? No takers? Okay. Continuing with the history of life on this planet that I'm not qualified to talk about, the there is a so th- we essentially went a couple of billion years without with essentially single-celled organisms that didn't have much ability to metabolize and use oxygen. There were certain organisms that were capable of using it, but they weren't very complicated and sophisticated. And those organisms became, at some point, our single cells ancestors. The I'm trying to get the scientific name here. There are two words I'm trying to say: prokaryotes and well, another word is
Eukaryotes.
eukaryotes. Thank you. And so the prokaryotes did not contain an organelle, which today we call mitochondria. Apparently, prokaryotes swallowed up one of these organelles, and these organelles were good at one specific thing, and that was using oxygen in a very sophisticated way. So we have our, our prokaryotes swallowed a organelle and became eukaryotes. And the eukaryotes then became much more capable of using oxygen. There's a very beautiful YouTube video that you should check out, which is called, which I don't know if that's what it's called, but it examines the mechanism by which these mitochondria create energy, and the energy source they use is a little chemical called ATP, which is remarkably sophisticated. And if you see this an animation of this chemical in action, you will find it very hard to believe that evolution could have invented this thing. It is beyond what you could imagine could have been created, randomly. It's you can't imagine this thing developing by natural selection, but nevertheless it did. So it's one of the more magical things that life has ever done, and you and every living thing on this planet could not survive without this incredibly sophisticated mechanism. So, so then you get, so then with this now addition of your mitochondria, multicelled more organisms can begin to be founded on this planet. And it takes another 2 billion years for these multicelled organisms to develop a backbone that will leave a fossil record behind. So, so 4 billion years spent gathering strength, and then the last half a billion years for the rest of history as we know it to evolve. Plants populating the land, animals leaving the oceans after another half a quarter of a billion years, another eighth of a billion years, or no quarter, and eventually what we have today. So evolution has produced the most amazing things in the last ninth of our Earth's history, but but it took 4 billion years for the good stuff to be invented before that we could put together the sophisticated organisms that we all know and love. That's not astronomy. That's just stuff that is, in fact, so much more interesting in some ways than astronomy, because stars and the rest of the universe, they don't really evolve. The laws of physics go, this is the rules you got to follow, and then the rest of the universe goes, okay, I'll do that. And they continue to do that for 13.8 billion years, and no really big news. Yes, we get some planets, we get some stars, but nothing really exciting happens until life gets invented. And then the complicated stuff arises. And then evolution, natural selection kicks in. Natural selection was not employed at all by the universe to create the universe that we have here. It was just a simple set of laws and they all followed them. Natural selection is beyond our understanding of how things work. So astronomy is cute, but biology is cuter. And I don't know biology. Now, is there anybody on the stage who'd like to?
Yeah,
Yeah.
but I hope astronomy would find why it is so cute.
Yeah, no, no, but I
It would
think it's
help
not necessary.
because, as you said, no, it is very difficult to know the logic behind this magical thing happening,
Right.
the phenomenon of life. But maybe astronomy can help in decoding that it is not just evolution, but something else is also there.
And I tend to think that what's going to happen is that in order to understand how life evolved, we're going to have to ask some pretty smart computers the question and get the answers from the smart computers. For instance, ChatGPT right now is a baby. And it doesn't know much, and it certainly doesn't have a good understanding of anything really. It just makes stuff up, but it's very smart as as a tool, and maybe it or some successor of it, we can ask it the question, how did life arise? and it could think a while and cogitate on all the parameters involved. Uh, you ask it, you ask something how to create, how to win at chess, and I believe that the computer programs that learn to win at chess got a little bit more intelligent than the people who put the stuff together put in the first place. And ChatGPT is certainly more intelligent than the pieces they put together, if you will. It's the future of human intelligence, and and so at some point we might be able to ask these supercomputers the question of how can you imagine how this happened, and then tell us how what the probability is of life. And that's the bottom line question that I think everybody wants to know. And I'd be curious as to why they want to know. But the question is, are we alone in the universe? I'd be interested. Listen, you can, all of you in the audience, can come to the stage and answer the following question, which is, why do you, as a human being, want to know whether there's life elsewhere in the universe? What is your reason, your personal reason, for wanting to know? So every one of you is qualified not to ask the stupid question, but to answer the stupid question that I just proposed, which is, why do you want to know whether there's life elsewhere in the universe, and especially intelligent life in the universe? Okay? So raise your hand. There's a little thing down at the bottom of your screen where you can raise your hand, and I will invite you. And I'm especially inviting uh, Carla, who has been in my room many times in the past and has come to us right now. So Carla, she came. I pressed the button. She came. Carla, can you answer my question? Why do you want to know whether there's intelligent life in the universe?
Well, I don't if I had a want to know, um I guess it would just be to understand the I guess the precocious nature of life itself. Um so I guess that would be my reasoning, because how well did the other life in the universe fare comparatively to ours? That's all.
Ah, so so how are you doing with your project?
Um, I'm doing pretty great. Doing pretty great.
Uh, Are you getting people to buy in and help you along with it? And you want to tell people here? By the way, I just a disclaimer. I'm not I'm not a fan of Carla's projects, but she has some interesting stuff to talk about. And so if you want, Carla, as a you can uh, tell us what you're doing.
Yeah, I would say Laird is an anti-fan.
Yeah, I'm an
However,
anti-fan. Yes, anti-fan.
however, I've got a question for you that relates, and I want to see how you. I guess I just summed this up kind of today. So, and I don't know if this is particularly astronomy, but it does relate to gravity. So I'm gonna go with that.
Okay.
So, so I guess it's an observation, but it's also posing to you as what your viewpoint is. So, okay. So basically, when you suck all the air out of a silo, you can allow the feather and the bowling ball to travel at the same speed.
Right.
But the argument is that they aren't traveling. The Earth itself is traveling, and they are not moving uh, as the universe around us is like not like basically not being forced. I think the point was. Um, but so then when they fall at a different speed, a rate of speed, the feather and the bowling ball, it's because of the resistance that the air
Right.
gives, right?
Hmm.
So then I, I finally,
But the first part of what you said didn't make sense to me. But the second part did. So yes, they fall at the same speed because of their lack of air resistance. But the first part, where you talk about something I didn't understand it. Okay, so go on.
okay, no worries about that then. But so I keyed into this little point where, okay, so, without atmosphere, without air, we don't see such resistance.
Right.
And to me, resistance is a means of making energy. And I'm pretty sure that through all respects, resistance is a means of transference, or,
I don't
you
agree, Carla.
you don't agree. Okay,
I don't.
cool, cool.
See, I did introduce Carla as a person that I would not agree with, so that's okay. So continue. Go
Okay,
ahead.
so whichever terminology you want to use, they do seem to be opposing each other. So, so in any case, I was thinking about it and I was like, okay, so would that mean that the existence of atmosphere, the just the existence of atmosphere, allowing for resistance um, to be like facilitated,
Hmm.
that is a means of producing energy?
No, but see, energy is first of all, energy is not produced. It's there's nothing produces energy. It's just energy is converted from one form to another. The amount of energy that is present in the universe is constant. So it doesn't get created, nor you convert mass into energy and energy into mass. I mean, given that business, that's why it's constant. You know what I mean? But you can convert any kind of energy into any other kind of energy. But resistance by itself isn't energy. It's simply it's simply the property that opposes motion. That's resistance. That's what it would say if you looked it up in a dictionary. The opposition to the movement of something. But in and of itself, it's not energy. When you work against resistance, you the motion that you have is converted into heat, because when you move against the resistance, you convert kinetic energy into heat energy. So you might say that it has something to do with energy, but in and of itself, it is not energy and doesn't contain energy. It just is a mechanism for converting kinetic energy into heat energy.
Okay, great. So converting. All right. So um it seems to me that this would be um a nice uh a nice way to understand the Earth's magnetic field. Um and that's what I see as the the converted energy is the Earth's magnetic field.
Well, the Earth's magnetic field is it uh, has more to do with the motion of a liquid iron core in a circular motion, spinning motion. That alone can create a magnetic field. That is, in fact, what does. You can take a globe in a laboratory that is conducting electricity, and you can spin it, and you will get a magnetic field. So I don't see the word resistance appearing in that scenario. Right. Yeah. But so and magnetic fields require, in order for them to be created, they have this little word called electromagnetic, and it turns out, surprise, surprise, that you can't have a magnetic without an electra. So electromagnetic, they come together in inseparable ways. So you can't have a magnet without electrons doing something. And so they have to be moving in some way to get something to be magnetic. And so the anything that is in fact a magnet, either permanent or created as a temporary magnet, is the result of the motion of moving electrons, but not
Okay.
friction, not friction.
Okay, but without atmosphere, without air,
Mhm.
how would the production of a magnetic field differ?
Well, first of all, the magnetic field is created deep in the core of the Earth, right? So basically, that doesn't know anything about the atmosphere. So uh, 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 it doesn't require an atmosphere has virtually nothing to do with the magnetic field of any object because it's created in the center of the object, not at the surface of the object. So,
Okay,
right?
but I'm asking specifically, like, do you know of examples where they have, you know, created magnetic fields without the presence of air?
Well, I'm thinking about that because the the mag- uh, I'm thinking which objects that we know of in our solar system have a magnetic field and don't have air. Uh, and I'm thinking real hard now, and I am unaware of any object in our solar system that has a magnetic field and doesn't have an atmosphere. The, 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 the objects that have magnetic fields are the Earth. uh, Mars used to have a magnetic field, but it doesn't any longer, and it has an atmosphere. Jupiter is has certainly it's all atmosphere, and it has a very strong magnetic field. Saturn has a magnetic field, and it's all atmosphere. Uranus has a magnetic field, and it's all atmosphere, mostly atmosphere, and Neptune mostly atmosphere and magnetic field. So those are the objects that I know of that have magnetic fields, and they all have atmospheres. But I don't think there's anything in that what I've said to even suppose that the atmosphere has anything to do with the magnetic field at all. In fact, and this is interesting, the magnetic field of Jupiter rotates at a different speed than the atmosphere does. So the atmosphere of Jupiter is, I think, a little faster than the planet itself spins, based upon the rate at which the magnetic field changes. Because we've been there, we've done that, we're there now, and we see that, if you will, the atmosphere and the magnetic field are not related. They're just associated.
Okay.
Isn't it the core that causes the magnetic field? The molten core?
Yes, the molten
So,
core.
hold on. So, if atmosphere is produced by trees and trees accumulate energy from the sun,
No,
then
no,
I don't
atmospheres are not created by trees. Oxygen is
atmosphere is not created by trees,
no, no, no.
plants.
Plants, plants in general convert one type of gas to another. So yeah, uh, so so th- so while there is, the Earth was very happy for 2 billion years without plants producing atmosphere. The plants did convert the primitive atmosphere that was found on our planet at the time of its formation into a different atmosphere. It sucked up the methane and ammonia that might have been there and converted it into oxygenated atmosphere. And look, nitrogen is not produced by plants at all. And most of our atmosphere is nitrogen. We're 20% oxygen and 80% nitrogen. and nitrogen is found on on all the other planets that have atmospheres, especially including Titan, which has which has the same proportion of nitrogen that our planet does. And there's no trees on Titan, so no, atmosphere is not produced by trees. Trees certainly have an effect on the atmosphere, and certainly are involved in the creation and production of oxygen in our atmosphere. But most of our atmosphere is nitrogen.
Okay, so it's also interesting to me that nitrogen is one of the things that plants and trees need in order to grow.
Right, but
So
it's very hard for plants and trees to get hold of that nitrogen. It takes it's nitrogen is notoriously hard to create compounds out of that can be used to fertilize the trees and whatever. It's a pretty difficult thing to do it. You know, lightning strikes do it, and very few very few inanimate processes are responsible for the creation of the nitrogen that plants need. So they essentially, so plants essentially invented on some level plants that would, whose job it was to put nitrogen in the soil. I imagine before the plants invented that nitrogen fixing plants, I imagine that plants didn't do quite as well uh, uh, as they do today.
interesting. Thank you.
Yeah, no, but but it's your point of view is interesting because you're trying to explain you're trying to explain and in fact engineer some change in the way people see and do things on this planet, right?
Sure. Yeah.
Right. So although I've always told you I disagreed with it, I think nevertheless I think that the energy that you have for this and the ideas, well, not necessarily ones that I agree with, are interesting nonetheless. And if you want to talk about them, I will try to keep my mouth shut to the extent of telling you. I'll only say every now and then where I disagree with you, but I'll mostly keep my mouth shut if you want to talk.
Oh no, I'm great. Thank you. Thank you very much for having me up here
Thank
and
you.
always remembering me. I won't get over you're always remembering me. It's fantastic. I do appreciate that.
Well, you know, Carla, I did something with you that I've never done in this room. I believe that I, uh, I took it upon myself to actually criticize what you had written. And it was a few years ago, and I was fairly ruthless in my criticisms, and I don't normally do that, and I just was kind of like feeling like, well, somebody has to slap Carla around, and I'll be the one. But I did, and I do appreciate the fact that you returned to my room, despite the fact that I was uh, particularly not gentle in those in what I wrote. I think so. I really do appreciate you coming back.
Yeah, you gotta love criticism because then I can just find the way that this works in a more palatable way for people to understand because I think it's just language and framing and um, some things that we maybe have out of place and um, yeah. But I mean, in general, what I found is that you know phytoplankton trees they create aerosols for clouds from the ocean and through
That's
the
true,
land.
and that is
And
certainly true.
uh,
And there's interesting. There's an article in this week's papers that are talking about the aerosols that trees create. Just this week, I believe. Have you seen it?
yeah, I saw it. So yeah, and this is something like I constantly am searching the news to make sure they're keeping up with it. But it's been really great because they've also talked about how microbes really contribute to the development of um, the ice. I think they were talking about in the Arctic, and how the living ecosystems contribute to how this ice forms and maintains. And so my entire point is that these living ecosystems are necessary, and we can't discount them. that's
And and
that's
I certainly agree with that. Certainly agree with that. And I think that the more we learn, the more surprised we'll be. And you're taking a very aggressive approach to what we should know about these living ecosystems. So yeah, and it's interesting because it does inform climate change,
absolutely, yeah.
right? Uh, you know, I had a personal relationship with the guy who invented climate change.
Ooh.
And when I say invented, I do mean that in just a humorous fashion. He was the head of the Goddard Institute for Space Studies in New York City, and his name is James Hansen. Do you know him?
No, I don't know that guy.
Yeah. So he was head of the Goddard Institute for Space Studies, and when I first met him, he hired me as a employee uh, to work on what his work was, and it had nothing to do with that. But after I left, he the institute that he was working at, the building on 112th Street in Manhattan, where I was working for a couple of years, they had a very big computer there, and they decided to use it for other purposes than we had used it, and they decided to begin climate modeling. So he uh, uh, became head of the institute and applied that computer to climate modeling. And so he was the first, uh, maybe not the first, but certainly the first I know of, to have modeled the Earth's atmosphere and its response to carbon dioxide. And he was able to, with his computer models, to show that the more carbon dioxide, the hotter the planet got. And that uh, made made him the world's leading authority on climate change. And he was he was he made all the news for a number of years, rattling his dice and saying we're playing dice with our planet, and eventually we're going to roll crap, and we're going to this planet's going to crap out. And of course, he's been proven to be right, uh, and um, and he's still alive, and he's still working in climate change, and the institute is still working on it. But the thing about it is that climate change, while being well established as being the result of human causation, still has problems with its modeling, because one very simple thing is, let's say you increase the temperature of this planet. Well, then what happens is you get more evaporation from the oceans. And if you get more evaporation from the oceans, then you get more clouds. And if you get more clouds, then the light is reflected from the planet, and then it becomes cooler. So the planet has a self-regulating negative feedback mechanism, and you can now bring in trees to your heart's delight in this scenario, uh, and talk about, well, if there's more carbon in the atmosphere, then trees are going to grow bigger, and they're going to produce more oxygen, and so that will reverse the amount of carbon dioxide in the atmosphere, and so again, negative feedback. So it's not as
Well,
simple as all that to invent a climate model.
one part that just seems fractured in our understanding is that we haven't seen an increase in clouds. In fact, we've had a decrease in clouds. However, there's more water vapor that's not in cloud mass in the atmosphere. So it's just hanging around.
Right.
So
because
Um,
because
so
because
that
hotter,
means there's a
hot,
flaw,
not
because
really, because water vapor is a greenhouse gas, and it can absorb, keep the planet hotter. And when the planet is hotter, it can hold more water vapor in the atmosphere without forming clouds. So it's not exactly unexplained. It's all part of the continuous mechanism.
or the
Hotter,
plants don't have
hotter,
what they need to
say,
create aerosols,
say again?
or the plants don't have what they need to create aerosols that would then make more cloud mass.
Right, it's because clouds are formed by forming around aerosols or, uh, or dust particles. And so if you have pure uh, uh, water vapor in the atmosphere, you're not going to necessarily get clouds. You have to do something beyond that to get clouds. Aerosols will help create clouds, and the aerosols also reflect sunlight. So all of these things are involved in the process of climate change. And so it's not as easy to model it as it may have been for James Hansen in 1972 when he was doing it. And well, he wasn't doing it in 72. I was working for him in 72. But let's say he was doing it in 1980. And it's a harder thing to model. But nevertheless, it's not, there's no doubt that the humans are the reason why the climate's heating up so fast these days.
No, no, that's a complete consensus.
Right.
We agree about that. It's humans' fault.
Except people who want, my best friend is among them, who feel that we should have hearings in Congress to determine whether or not this is true. And I find that to be specious
Oh,
because I think that Congress
to,
is not a place to determine truth.
I'm sorry, to determine what I didn't.
To determine truth.
But what did he want argued in Congress?
He wanted Congress to hold hearings on climate change and to determine whether or not climate change is caused by human intervention. Because many Republicans hold to this day hold out that climate change is not the result of human interaction. So since my friend is a Republican, he he was he felt that the only way to determine whether or not there's a truth here was to have it brought up by and investigated by Congress, and that's not the way you figure out science by subjecting it to
Hmm.
hearings. I mean, how do you figure out science in the first place? How do you figure out science? How is something become true in science? And it's not a simple thing. In fact, the best explanation I've ever heard for how things become true in science is people who don't believe it die off. So the non-believers die off, and the new believers take the stage. And so some people are never willing to give up the ghost. I had my advisor at Cornell. His name was Tommy Gold, and he and another guy who's more famous, Fred Hoyle, together invented the steady state theory of the universe, in which he hypothesized that the universe had always been and always will be. And the fact that the universe was expanding, which was known at the time, he had no problem with it. They said that the universe is simply producing stuff out of nothing. And how do you know that's not true? Huh? And and the and for a long time there was no proof that that they weren't right. But eventually they discovered the cosmic microwave background radiation, and that put the nail in the coffin. But not so fast, because at least Hoyle, I think, if not Tommy Gold himself, held on to their belief that or at least their hypothesis that the of the steady state theory of the universe, and the way that the theory has fallen into disrepute is that both of those guys are dead now. You know, so so certain things don't become true because there it's just consensus. It also takes a lot of people dying in order for it to happen. For example, let's see another thing. That's all I can think of right now in the moment. But so certainly Congress shouldn't vote on whether or not climate change is real. They should take the advice of experts. But you can always find an expert who says the opposite, and they do. There are real credentialed people who have, who I believe have said that climate change isn't human produced. But these people, in fact, if I'm not mistaken, are also less than well qualified to say these things. You know, they just have PhDs. But a well-known PhD who invented something called the Pauli exclusion principle, a very important law of physics, and who won a Nobel Prize for having figured this stuff out. Uh, he later became the world's top guru in saying that vitamin C can prevent the common cold. And this guy, speaking alone in the darkness, managed to convince lots of people of the truth of what he was saying, even though he was literally a quack. And so if you look up to this day uh, the ability of vitamin C to prevent the common cold, you will find very little support for that point of view. Nevertheless, throughout the 60s and 70s, 80s and 90s, and maybe even to this day, people still believe that vitamin C can prevent the common cold. Does that,
Right.
right? Do you believe that? Does anybody in this room who's on the stage believe that vitamin C can prevent the common cold? Because uh, because in the '60s it was all the rage. Even I who took some extra vitamin C, but I was among those people who were told that this guy didn't know what he was talking about.
But don't you think a vitamin C deficiency would make you more vulnerable to, affect your immune system so you more likely get a cold?
A vitamin C deficiency will produce scurvy. Not to
It,
mention, some other diseases that may be more obvious. But no, I don't know that there's any benefit from more vitamin C than the body needs. You know, our bodies don't produce that vitamin, so we need to do it ourselves. We need to get it externally, but our bodies used to produce vitamin C, and I think many animals on this planet produce it, so they don't need to have an orange every day.
the next time
You
they
know.
advertise for vitamin C, they need to say, "This way you don't get scurvy."
Yeah, well, right. Don't scurvy, right? Or D, vitamin D for rickets. Right? We used to produce vitamin D. You know why I don't know if this is true, but I like the story that the Vikings tried to populate Greenland, and they didn't succeed. And the reason they didn't succeed is because they made a little mistake. Uh, they you used to fish for codfish, which have lots of vitamin uh, D, but then they started raising cattle and eating the fruit of the land rather than of the sea, and the cattle didn't contain any vitamin D, and they just simply died off. So cod liver oil is really good for you in small quantities. Come on, people in the stage, are you
Yeah.
in the audience? You're not raising your hands. We need volunteers up here. Uh,
Hi.
okay. Yes. Hi, Jean
Hi,
Frederick.
hi, Laird. No, I was just going to say, even here in Florida, Tropicana does not market oranges as vitamin C, with as preventing the common cold. And you know that if they could, they would. So
That's interesting. That's interesting. Yeah. No. No. I didn't know that. That's interesting. Uh, and so uh, I'm curious as to when Linus Pauling uh, be, fell out of favor. In other words, his history of disappearing from the common speak. When did that happen? You know, uh, Carla, you're doing these cool things that I can't see what they are when I press the button. Those are cute
Oh
cartoons you're
no.
putting up. No, I can't see them when I
Just
press the button.
reacting.
Ah,
There's a pirate. There was a chili pepper. Chili
I
pepper's probably
easy.
better for
That I can see.
colds than vitamin C.
Right. No, it's interesting because when I touch the icon to make it bigger, all I see is the picture of you wearing headphones, and I don't see the picture of all the little cute things you're adding. That's just a defect of the app. Uh, so,
Vitamin
uh,
C is marketed as supporting the immune system. There's a there's even a product called Emergen C. It's like a thing you mix with water.
well,
It's a
supporting the immune system is a claim that is probably true. The question is, how much does it take? There are a number of other things that don't work.
So,
Uh, uh, and they are sold in drugstores. Airborne, I think, is a product that doesn't work. And there's a thing that helps prevent the flu. I forget the name of it. That doesn't work. They really, I mean, they get away with this stuff because Congress doesn't stop them. They don't produce a law that's strong enough to stop them from marketing this stuff. As long as they make certain claims, they can get away with it. And so there's an awful lot of misinformation available to the common person. In fact, as a scientist and as a professional skeptic, uh, I constantly I spend my days reading things that I don't believe because they're basically lying to me most of the time. And if not, in the mostly they lie in the headlines. The headlines are the thing that does the most lying. And when you actually read the articles, they tend to be less of a lie than usually they lie by saying something like, is this true?" And that's how the article is phrased in the headline. And then the and then when you read more carefully, the the story actually says, "Well, we don't know," or maybe it isn't. So they can lie just in the headlines. But anyway,
Laird, I just wanted
yeah,
to pose a question, and I'm reacting to
sure.
quite a ways back in the conversation about magnetic fields. My quick Google search says that apparently Mercury has a magnetic field, but no atmosphere.
I think yes,
So
that's I was not clear on that, so I didn't
yeah,
say it.
it's not strong. It's 1% of Earth's apparently, but according to the Messenger probe, they figured that Mercury has not an induced, but an actual dynamo magnetic field,
Right,
and no atmosphere.
but here's the thing about the dynamo magnetic field of Mercury. Mercury is rotates, okay, and it rotates. It's not uh, it's not tidally locked to the sun,
Right.
which you might expect,
Okay.
but it actually does a thing. It does a once every other rotation. uh, it presents one face and then the other face to the sun. So it rotates a little faster than you might expect that it revolves, but it doesn't rotate very fast. So the fact that it has a dynamo created magnetic field was something I didn't remember or
Oh.
or think because I didn't think it rotated fast enough to produce a magnetic field, and I forgot what they had actually found.
So
And
is the reason magnetic field that
Jeff Frederick, you have You
Oh my
always
God.
have a signal loss when I'm talking to you. Do you have that in the rest of your life? That when you're talking,
No,
that
it's just Clubhouse. Clubhouse is
it's.
the only app that hates me.
I
Um,
see. Say
no,
it
but
again. Say it again.
I just is the reason that Venus does not have a magnetic field that it doesn't rotate fast enough.
I think the answer to that is yes. That's I've always thought that, and so I uh, and well, but then yeah. So yeah, I'd say that's the answer. But I don't know
Cool.
if it's in fact scientifically, if you will, dogma. But it's certainly probably true, for sure. The things have to rotate in order for it to make a magnetic field. Mars rotates. Why
And
doesn't it have a
on top of
magnetic
that,
field?
Mercury is smaller planet, right? It doesn't have the core would be cooled down, and how come it can able to make a
Well,
dynamo?
well, Mercury is made up of a much more of the Mercury is in fact uh, uh, made of heavier materials, such as radioactive materials. So the fact, even though it's small, it contains more uranium than, let's say, Mars does, because Mars formed further out, where it had some of the rocky things that that Mercury does not have. I'm not sure of what I just said. I'm just hypothesizing. So Mercury has more uranium than Mars does, and so it's hotter inside, and so it hasn't lost its magnetic field. Mars, on the other hand, is a larger planet than Mercury, but nevertheless, it has lost its magnetic field, probably because it cooled down over the millennia, the billions of years, so that it doesn't any longer have a magnetic field. I have seen places where it was said, and I haven't seen it recently, where it said that Mars has been shown to have had a magnetic field in the past, but I haven't read that recently. The same way that you can see that the Earth has had a magnetic field in the past by looking at the stripes in the ocean's mid-Atlantic ridge, where it goes like stripes, north north, north south, south north, north south, south north. So that is how we see the Earth's magnetic history. But on Mars, I think they saw a similar phenomenon, but as I said, I haven't read it recently.
Actually, I just thought of was thinking about Carlos' question about the magnetic field. I think there is a point. I mean, certainly the magnetic atmosphere is not produced by a magnetic field, but magnetic field does protect the atmosphere because the solar wind, the high energy, the electron can knock the atmosphere, the molecules out of the orbit of planet, out of the gravitational field capture of the planet. So when you do have a strong magnetic field, these electrons will be captured, will be basically rotating along the magnetic field line, especially when it's kind of a toroidal, because well, it's the any planet would be a sphere, or approximately a sphere. So the magnetic field line was a toroidal field, and then you have strong and weak uh, field around the planet. So basically, the electrons, charged particles, would be captured, so they don't have a much less probability of hitting the atmospheric molecules. I'm done.
Okay, so Hanson, so this is all very good, and I see by your profile that you are a theoretical physicist, which is terrific. I can engage you in this little question that we're engaged in right now. Okay, so two planets on the table. I want to put Mars on the table and Venus on the table. And and I want to ask you this question. Would you agree that the absence of magnetic field is responsible for the lousy atmospheres that these planets have?
Yes, I would think so.
Right. So, so now let me ask you this question. And this, by the way, it was a way that I spent one entire year of my life. I'm 78 years old. 1 year of my life was devoted to the answer to this question: how did Venus lose its water? And I did not succeed in beginning to answer that question. But I wonder if you would venture to suggest an answer.
How did Venus lose its water? I think Venus is pretty hot, right? And then
Well, it didn't start out being hot. It was a nice place to go on vacation.
sure, I think
Sure,
the
probably had water.
yeah, I think it has the carbon dioxide and oh, maybe well actually, well, how does it lose water? That's a good
Lose? How
question.
did it
Actually,
lose its
evaporate.
water?
Well, yeah. Okay, so it probably the I know the Venus has a thick atmosphere with mostly composed mostly of carbon dioxide. It
Right.
could be the greenhouse effect.
Well, no, but see,
Um,
which I'm
but
asking you how it lost the water, now
yeah,
how it
no, no.
got,
I was just
not
thinking.
how it
I
got
know.
hot.
I'm right. I understand. But I'm just right now just completely thinking. You know,
Oh,
putting ideas on the table. Could
well,
it be that?
it was a trick question because you already gave the
Oh,
answer.
maybe. Okay, so it knocked the vapor out of the solar wind knocked the vapor molecule off
Yeah,
the planet. Well,
right.
but then how did not? Okay, maybe it is water's more um, the absorbent of photons than the other gas molecule.
Well, look at this:
And
carbon dioxide, right? Carbon's heavy,
yeah,
oxygen's heavy. Hydrogen dioxide is, in fact, contains hydrogen. Hydrogen is not very good at staying around planets that don't love them and protect them with a magnetic field.
yeah.
But
So,
how did it
but
separate
I'm
from
trying to think.
how did it separate from water?
Say again?
How did the hydrogen separate? Uh,
Well, see that you get
what?
Yeah,
ionizing
because
radiation from the sun.
right.
The sun ionizes the hydrogen, it either by direct impact with protons from the sun because there's no magnetic field, or ionizing radiations from the
Oh,
sun via ultraviolet
yeah.
that
Actually,
could
because
ionize hydrogen.
right. Actually, that could be the uh, because the hydrogen bond to um, the oxygen is kind of relatively weak, and then when you have a high energy electrons, it's easier for the hydrogen to be knocked off than other molecules. The energy required to decompose other molecules.
And then the gravity of the planet and is not strong enough to hold the protons in thrall, and the solar wind can pull those protons away because of the lack of magnetic field, and boom, you lose the hydrogen, and you lose the hydrogen. The oxygen goes elsewhere and finds another home for itself.
Yeah, it's kind of pretty selective though. I left all the uh, the other uh, components of the atmosphere alone and are not doing too much damage, but only the hydrogen.
Well, then there's another little problem. Okay, so on our planet, if you take all the limestone and the carbonates that are found in the ground, and return them to the atmosphere from which they came, the Earth and Venus would have the same amount of carbon dioxide in its atmosphere, but on the Earth, we had sequestering of carbon dioxide in limestone as a result of life forms as well as simply natural processes. So uh, we sequestered our limestone on Venus. They didn't. So it's all in the atmosphere
Who's
because
they?
there was no water. There was no water to sequester the carbon dioxide.
I
Mm.
just read that Venus, the atmosphere on Venus, the air pressure is 90 times that of Earth. Why
Yes.
is that?
Because if you returned the carbon, if you return the limestone on our planet to the atmosphere, you'd get the same density that of atmosphere that Venus has. Now, I've read this. I'm not perfectly certain that this is a good story if it's not completely true. But I believe the story because I've told it many times without fear of contradiction, and I haven't read anything that really contradicted it. But as I said, it was my job for a year to ask and answer this question, and I needed to. And the way I answered it, as I said early on, our sun produced an awful lot of radiation in the form of a solar wind, which could have blown away the atmosphere of Venus in its early stages. But I wasn't able to prove that. It's sort of true now that that we know that the sun was early on a very nasty parent for our solar system and produced a lot of ionizing radiation in the form of a solar wind.
Oh, well, the study. So
Yes.
sorry. The study that they did out of I think it was New Zealand about the Kodi trees and how they saw that changes in the magnetic field also coincided with climate change. What you're saying supports that. And it's interesting because NASA has really come out of their shell to proclaim that that's not the case. But if we see that changes in a magnetic field can then perpetuate atmospheric loss, then I don't see why those things aren't, you know, um, in agreement.
Well, the Earth's magnetic field has, over time, reversed its direction, but I am not aware of any thoughts that the Earth's magnetic field has disappeared. I think it in the is has changed the direction in which it points without necessarily diminishing in its intensity. So I think the Earth has always been protected by a magnetic field. And if it hasn't been for some short periods of time, those periods of time were not long enough to contribute to any climate change.
Okay, the study's in the chat though, if you want to see that.
Oh, let me see. What do we have? Ding, ding, ding. Oh, we have
Laird,
chats.
does it literally alternated that North Pole and South Pole, or just changed its direction?
Say that again.
I mean that magnetic direction is changed. You said right, as you said, that's literally just reversed or just changed its angle. I mean North Pole and South Pole.
So I'm seeing, Carla, I'm seeing that 41,000 years ago, uh, trees in New Zealand revealed that there was substantial increase in carbon 14 because the weakening of the magnetic field. Okay, I'll buy that. Absolutely. Why not? But I don't know that that contributed to climate change at the time. It may have, but I don't know.
Well, I guess the key word would be weakening, and so if the strength of the magnetic field is not in a stasis, then there can be potential losses. That's what I'm thinking on a scale.
I just don't think it had. Listen, at the time, nobody cared. At the time, nobody cared because there was nobody around to raise an alarm. Even though there were people on this planet at the time, uh, the fact that there was a slight change in climate has been changing on this planet for a very long time, forever, and and what's happening now on this planet is unusual in the rapidity and the intensity, but otherwise,
Well,
climate change is normal.
and that's exactly why I want to challenge how we think conceptually the magnetic field is being created, because I think that is where we have an issue. And it's not completely, you know, immediately available as far as, looking out at other planets and making comparisons. There are other factors we may not see on surface level. But that's exactly why, I really have to, I, I, I I must continue to do the thing that I do.
Yeah, but right, but we can't, we have no influence on the magnetic field of the Earth. It's going to do what it's going to do, right?
I actually do not believe that. I don't believe that.
That's where we differ.
Yep,
That's
yeah.
where we differ, right? Right.
Because yeah, I do think there's an active there are active changes that have to do with what is on the surface of the earth, what is on the land, what the land is made of.
Oh, right,
Um
for certain, for
the
certain.
magnetic particles, every single one. So, the changes in how we're using iron, for instance, and accumulating it for ourselves in different areas, how does that affect our iron core? And does it affect our iron core? And how, the yield of energy, um, that's I'm at conversion, whatever word you want to use, the conversion of energy from these specific factors. I'm thinking about all of those things.
Well, if you compare the surface of the Earth to the surface of an egg, forgetting for a second that an egg is oblate, and just pretend the egg represents our planet. Uh, the roughness of the surface of an egg is much rougher than the surface of our planet. If our planet was reduced to the size of an egg, and you held one in your left hand, the Earth in your left hand, and an egg on your right hand, the Earth would be a lot smoother than the egg in your right hand. In other words, what we do on this planet is just minuscule in terms of the planet itself. We have nothing, we have no effect on what the planet itself is doing. We can't change anything except the atmosphere, which do have some effect on, but not what's going on no, beneath our feet. No way.
Well, yeah, I think there are things. I think there are things that take place that we might dismiss because they seem small, but I think that they're vital. So, for instance, like the top parts of the atmosphere are cooling, and so as much as we're saying, okay, well, there's carbon in the atmosphere and it's heating things up, the opposite may be true of where the carbon once was, right? So would you'd want to look from the other perspective. So if the carbon were in the earth have um, would have the warmth that it needs to keep the upper reaches of the atmosphere warm. And that's how I'm thinking of it.
I,
And
I,
also, of course, the
I,
water vapor would be
Can I
inside.
run
I
with
think,
this just a tiny little bit?
please,
The carbon was in the earth.
right. That's right. And you
Yeah.
do mean carbon,
what
and,
what's
and,
your
and,
point,
and you
Alfred?
should and you should say carbon dioxide if you mean carbon dioxide. because the atmosphere of our planet doesn't have carbon per se; it has carbon dioxide, right? So, uh, and carbon, but you said carbon, so I was
Well,
confused.
so imagine you let go of all of the heat retaining uh, sequestered carbon, and that heat retaining sequestered carbon floats to the atmosphere,
No,
but no
wait a sec. Wait a
longer.
sec. There's no sequestering carbon in our under our feet. Okay, and there's heat sequestering carbon dioxide over our heads, right?
Laird, do we have an idea of how much extra carbon, atomic carbon,
Yeah.
is actually in the atmosphere associated with the carbon dioxide? And if we could magically dissociate the oxygen from the carbon, what would be the thickness of the soot layer which would fall back to Earth?
That's an interesting question, but I don't think it'd be
Because
very thick.
it
I
wouldn't
don't
be
think.
very thick, but that's kind of the point. Is like
Okay,
if you evenly distributed all that carbon
I
all
can
over the
tell. I
Earth.
can actually. I can do a little calculation with you. Okay,
Hmm.
how much does the atmosphere above your head weigh? Really, you know the answer to that.
Well, one
14,
atmosphere,
14 pounds.
14
14
pounds, yeah,
pounds per square inch.
per square
That's
inch.
what
Yeah,
it
that's right.
weighs. That's why it's the air pressure. If you have a column of air all the way up, all the way out, that column of air weighs 14.7, I think, uh, pounds in a square inch. Okay? That's how much. Now, imagine that you take 14.7 pounds, okay, and most of that is 80% of that is nitrogen, and 20% of that is oxygen, okay, and well, 1% is argon. Did I leave out anything? Yeah, I left out some carbon dioxide because it's really not matters. So, of the 14.7 pounds of air above my head, maybe a couple of, maybe less than a gram is made up of carbon dioxide. So I could essentially, uh, I can answer your question. If all the carbon dioxide in the atmosphere was dropped down on the Earth as a solid, it would be less than a thin candy coating, and certainly less than the thickness of the shell of an M&M. So I've answered your question. It's
Yes, you
nothing,
have. Yeah, right.
right?
So it's the fact that it is not elemental carbon that is somehow magically thermally, a thermal blanket. It's the fact that it's been turned into essentially uh, carbon styrofoam.
Yeah,
Right.
yeah. And yeah, so carbon in the atmosphere is really nasty. Methane even worse. Water vapor, of course, has its does its job as well. And then there are other things in the atmosphere. There's aerosols, like Carla says, and clouds. And as you go up in the atmosphere, Carla was referencing temperatures higher in the atmosphere. Uh, as you go up in the atmosphere, things happen that you wouldn't think would be happening. So, for example, as you go higher, it gets hotter. Now, it's true that it gets colder. So, if you're flying at the level of a jet plane, it's really cold up there. But if you keep going higher, it gets really hot. Does that mean that you can make roast marshmallows because it's hotter than boiling water and hotter than and it's really hot up there. But what happens? It's hot, but it's not. But the atmosphere is not thick, so you still freeze to death. But it would be hot, like the temperature of the sun's atmosphere is 2 million degrees, and in the corona, but you still freeze to death unless, of course, you were basking in the rays of the sun, in which case you'd fry. But if you were hiding behind a sunshade, you'd freeze to death in the $2 million degree corona. So yes, it gets hotter as you go up, and if the temperature in the outer layers of our atmosphere are changing, that is interesting because that does contribute to the loss of our atmosphere. But we're not losing atmosphere at any rate that's worth talking about. So climate change is not going on in the upper thermosphere. And it's called the thermosphere.
So in the interim, and unfortunately, I can't post this to the chat anymore because there is no more chat. Oh wait, no, here it is.
Yeah, it is.
I didn't find the chat. So I'm going to paste. No, I can't paste. Okay, it's
Yeah.
not pasting. Anyway, ChatGPT responded to the same question I asked you, 0.034 millimeters, so 0.03 millimeters of soot. And
ChatGPT sometimes gets these things wrong when it
I
does
know,
math.
but it gave me 7 steps, and it did the math, and I was just going to, just for shits and giggles, post this over here to see if anybody wants to, mess around with this. But anyway, it was just
That's
really funny.
that's interesting.
But the other question was, and this might be really really stupid. It probably is. If I imagine Venus being sandblasted by the sun, losing its hydrogen, how fast is that hydrogen escaping, and what is the probability that some of that hydrogen got swept up by the Earth?
Zero probability it was swept up by the Earth, and
Okay.
I mean, just it's look at Venus. It's a speck in the sky, right?
But I'm visioning this cloud of particles just getting blasted off and then winding up, eventually crossing our orbit. And then you've got this Earth Zamboni coming through and potentially catching some, but not much. I don't
Well,
know.
occasionally when the winds were right, perhaps it did, but I don't think much has happened. Listen, Hanson, Frankie, I didn't talk to you at all tonight, and Firos, I didn't talk to you at all tonight. But Hanson, I want to thank you for being in the room. You're really helpful, and I need to acknowledge and talk to Firos and Frankie, and then quickly Jack. But I do want to end the room soon. So, Firos, you're next, and if you have nothing to say, and Frankie, you have nothing to say, I'll end the room soon. Go ahead, Firos and Frankie.
Hey, so going back uh, to one of the first questions in the room, um, I left and came back, and something was kind of perplexing uh, about orbiting the Earth. You talked about equatorial orbits
Hmm.
and how certain things need to maintain an equatorial orbit, but if you're in a geosynchronous orbit,
Has to be
uh,
equatorial, yeah.
uh, well, something could be orbiting at a rate that's not geosynchronous, right?
Right, certainly.
So, um, how do you reconcile, or how do I reconcile the idea of the Earth wobbling while the object orbiting has its own mass and doesn't? How does the Earth have a lateral influence or a longitudinal influence on anything that would have to maintain an equatorial orbit? Does that make sense?
Not quite, but imagine the Earth is a point at the very center, and to a very good approximation, that is absolutely the way it's done. The Earth is just a very, very small dot at the very center of its mass. And so now you talked about a wobble, but that's a very small effect, and it evens out over time. So whatever wobble you're referring to, and I'm not aware of it, it's still not important.
Well, we have a seasonal pitch, right?
The,
Uh,
the Earth does all sorts of things that it doesn't spin perfectly right, but
right,
it's but over time it averages out to a perfect spinning top that doesn't change except over millions of years.
right. But an object, even with a small mass, orbiting the Earth could have a polar orbit. You know,
Polar orbits are polar orbits. They just don't. They're not geocentrics. Geocentric
why not?
because the Earth spins underneath it.
but it has the same mass regardless of
No,
its
it can be 23.
regardless of its angular velocity,
It
right?
can be 23,000 miles up, but it will not station keep above the same spot on the Earth as something that is in equatorial orbit around
Okay,
the Earth.
right. It wouldn't keep the same geographic points,
Right.
but it would maintain the same orbital velocity.
Yes, of course. So it could be made to travel once around the Earth every 24 hours.
So I guess my question is, does the Earth have any influence on an object with some small mass that that influences it other than its orbit around its logical center?
No, the way you do these calculations is you assume the Earth is a
Right.
dot, and the spacecraft is a dot, and you do the calculation, and then
So if
then
the
there
Earth
is
wobbles, then the object orbiting the Earth would not.
this wobble you're talking about. It's a very small effect. It has to do with seasons and
Right.
ice and where the ice is on the planet and stuff like that. But these things I think, are very minor effects compared to the very major 24-hour thing. And these spacecraft have the ability to move and from where they are to get to compensate for whatever they need to compensate for.
I see. Okay. I think that's the dumb part of my question is they do have the ability to correct for the pitch.
Right, but I
Well,
don't
well,
know.
well,
I don't know to what extent that is necessary. I'm just saying is if you insist that it's necessary, then they can do it because they got rocket motors on board.
yeah. I mean, so it's in really, really, really small. I mean, it's not really wobble. I mean, it's wobble is really, it's like a tenth order correction or something. Uh,
Right,
Probably the only thing that could be a little bit different from a dot, these computed from a dot, is it's probably a spheroidal shape because it's slightly flattened at the equator because of
right.
the centripetal force. But that's probably the next order for correcting the gravitational pull. But that still is very small. But and yeah, they very very small.
When they do the orbits of Earth satellites, they don't assume the Earth is round or sphere. Or even an oblate spheroid. They compensate for mountain ranges and oceans, and they compensate for all that stuff because in the end, those orbits make slight changes over time, and they have to accommodate that, and so they build a model of the Earth that is no way spherical. But those are effects that occur over a long period of time, meaning weeks and years, and things way up high are not as affected because they're quite a distance away from these imperfections in the Earth. So the only things close to the surface of the Earth would be require constant monitoring.
Yeah, I mean it's more constantly monitoring correction for low orbit satellites, but the low orbit satellites has more more impact, suffers more impact from the atmosphere, the edge of the atmospheric friction than the gravitational irregularities from or deviation from the sphere.
Right, right. So listen. So if Firos is not here, I want to in the room soon, and I want to give the final word to Jack. Jack, you're here.
As well as you should always do that
Yes, right.
on and off the clubhouse.
Thank you, Jack. Right.
I have nothing of that
Okay.
of any of real interest to say except for this as a chat GPT update. Um, Now that it's connected to the internet, I did a search and it finally knows who your award-winning daughter is.
Really?
Uh, if you
ChatGPT
type
knows my daughter?
So, for instance, if you type in Tara Tadros Whitehill, it actually gives an accurate description
Really?
about who she is.
That is impressive.
On the other hand, it still has no idea who I am or you are.
Right. I am not impressive. I would love to leave this planet with a Wikipedia entry, but I'm not looking. And it's not looking good. It's not looking good. Uh, but who knows? That's good. Yeah. So you can all check out my daughter Tara Todris Whitehill. You can chat GPT her, and with that, I think I will end the room. Uh,
Go to bed, Grandpa.
Thank you. Orion, my grandson, who used to in the room, is not awake now because he lives now 5 hours ahead of me rather than seven, and so he's not awake yet. So, thank you, Jack. I will end the room by doing what Orion used to do for us all and counting down. And so I will count down from 10. He used to do it from 20 backwards in Greek, but he's not here. So we will do it, and you can join me if you like. And I'm going to be starting to count down from 10 and 9 and 8 and 7 and 6 and 5 and 4 and 3 and 2 and 1, and we're gone.